Quantum networks of clocks open the door to probe how quantum theory and curved spacetime intertwine. Quantum networking is being rapidly developed worldwide. It is a key quantum technology that will enable a global quantum internet, the ability to deploy secure communication at scale, and to connect quantum computers globally. The race to realize this vision is in full swing, both on Earth and in space. New research and collaboration between Igor Pekovsky at Stevens Institute of Technology, Jacob Covey at the University of Illinois at Urbana-Champaign, and Johannes Beauregard at Harvard University suggests that quantum networks are more versatile than previously thought. In the paper titled Probing Curved Spacetime with a Distributed Atomic Processor Clock, published in the journal PRX Quantum, the researchers show that this technology can probe how curved spacetime affects quantum theory, a first test of this kind. Quantum physics has passed every test with flying colors so far. But how it behaves when Einstein's theory of gravity general relativity comes into the picture is less clear. In Einstein's theory, gravity is no longer a force, but a result of changing space and time-curved spacetime. This leads to unique effects, such as the slowing of time near planets. The phenomenon has been measured and confirmed to very high accuracy. As well as popularized in science fiction films and novels like Interstellar. But how does this changing flow of time affect quantum mechanics? Could quantum theory, or general relativity, or both, require modification where they intertwine? While a full theory of quantum gravity remains lacking, there are suggestions that quantum principles might change in the presence of curved spacetime. However, probing this frontier was so far impossible in experiments. In a previous study titled Testing Quantum Theory on Curved Spacetime with Quantum Networks that appeared in Physical Review Research, Pekovsky and Beauregard showed that the time is ripe for experiments to explore these questions using quantum networks. They showed how two unique but distinct features of quantum theory and gravity come into play simultaneously. In quantum theory, there exist superpositions. Matter can exist not only in specific definite states, but also in mixtures of them at the same time. Quantum computing exploits this fact to build qubit superpositions of bits of 0 and 1. Then, quantum networks can spread such qubits across large distances. But in the vicinity of Earth, these qubits would also be affected by curved spacetime because the flow of time itself changes. The researchers showed that superpositions of atomic clocks in quantum networks would pick up different time flows in superposition, and that this opens the door to probe how quantum theory and curved spacetime intertwine. The interplay between quantum theory and gravity is one of the most challenging problems in physics today, but also fascinating, says Igor Pekovsky, Jeffrey S. Inman Jr. Professor at Stevens Institute of Technology and one of the authors. Quantum networks will help us test this interplay for the first time in actual experiments. Teaming up with Covey's lab, Pekovsky and Beauregard then developed a concrete protocol. The team showed how quantum effects can be distributed across network nodes using so-called entangled W states, and how interference between these entangled systems is recorded. Discover the latest in science tech and space with over 100,000 subscribers who rely on phys.org for daily insights. Sign up for our free newsletter and get updates on breakthroughs, innovations, and research that matter daily or weekly. Email by exploiting modern quantum capabilities such as quantum teleportation and entangled bell pairs in atom arrays. A test of quantum theory on curved spacetime can be achieved. We assume that quantum theory holds everywhere, but we really don't know if this is true, says Pekovsky. It might be that gravity changes how quantum mechanics works. In fact, some theories suggest such modifications, and quantum technology will be able to test that. The results of Pekovsky, Covey, and Beauregard demonstrate that quantum networks are not only a useful practical tool for a future quantum internet, but that they also provide unique opportunities for the study of fundamental physics that cannot be achieved with classical sensing. At the very least, a test of how quantum mechanics behaves on curved spacetime is now possible. More information. Anonymous. Probing curved spacetime with a distributed atomic processor clock. PRX Quantum. DOI 10.1103. Q188B1CR. Johannes Beauregard, ETAL. Testing quantum theory on curved spacetime with quantum networks. Physical Review.